All right, we'll go ahead and get started. I guess people are busy getting stuff done before spring break. Today, Keane's going to be giving a talk about systems reverse engineering, and then we'll go to beginner's night that I'll do on cross-site scripting, so some web vulnerability stuff. And that's all we have planned for this week. We won't have any meeting next week, obviously, it's spring break. And then after that, we'll be in here again. Yeah, but the one after that will be in another place, but I'll email you guys about that. Yeah, you good?
Yeah, should be. All right, so I'm going to talk today on systems reverse engineering. So let's get started. As usual with my talks, if you have any questions, feel free to stop me, yell it out. If you're confused about anything, let me know if you want more detail. I'd be glad to answer your questions or explain further. So getting started, we had a previous talk by Logan, who's not here, on reverse engineering, specifically binaries. So we looked at ELF files in Linux, how to disassemble them, look at what the assembly code looks like inside them to try to figure out what they're doing. We also talked about decompiling, so getting your machine code back into some semi-readable language like a C pseudocode sort of thing. I'm not sure if you talked about debugging at all, but that'd be like, you can run a process and look at what's in the registers and what's stored in memory and stuff like that, try to figure out how it's working behind the scenes without having the source code. So we're not going to talk about that stuff as much. We're going to talk about more of a system level focus. But first of all, why reverse engineer something? Well, first of all, reverse engineering, the primary purpose is to try to reproduce it or try to figure out how it works at a low level so you can kind of replicate that functionality. And a lot of times you'll see like jailbreaks, so like there's a PS3 down there, there's an iPhone. The way those jailbreaks are developed are by people who reverse engineer these platforms and figure out how they operate, how the firmware update mechanisms work, stuff like that. So people spend a lot of time trying to do that. Another reasons to find vulnerabilities, a lot of companies have bug bounties not only for their software but for hardware as well. So you might have heard of the G-Packers. They got pretty famous at DEF CON and on the news as well, by hacking into a Jeep, controlling it remotely, and crashing it into a ditch, stuff like that. And that was done by reverse engineering the car's infotainment system, which was a Unix machine. Additionally, if you're just curious, a lot of stuff can be cool, and learning how it works is, by diving into it with RE, is a pretty cool way to find out how something works. If you've got a device around your house or something, you just want to figure out how it works, what's going on behind the scenes, RE is a cool way to figure out what's going on. And as I said, it's fun, so you should do it. So we talked about binaries, and binaries are a good goal to get to with reverse engineering because you can see exactly what's happening in the execution, see what the program's doing. But what if we don't have binaries? What can we do? So we're going to talk about bigger scale, as I said, not really binary focused, but more about the system itself. So what is a system? It's kind of a broad topic here, I guess, but a system is really anything that can take input and do something to it and throw out an output. So examples of systems, pretty much anything. So I've got computers, operating systems, smart devices, like a smart lawnmower, fridge, cars. Anything we want to think of can be a system. Big or small, we're going to call it a system, and we're going to look at how to take a look at these sorts of things. Not just one binary, one program. We're going to look at bigger scale entire systems. So if anyone's in 538 or has been in 538, this will sound a little repetitive, but we read a paper in that class about attacking systems. And this paper is actually from 1975, but it still applies today to modern systems as well. The first step is to figure out what's going on, how it works. So they say learning system control structure. Just kind of learning how the parts of the system interact and what they do. The second step is you generate flaw hypotheses. So you might find a component, let's say you're looking at like a website or something, and you've got a field that lets you ping an IP address. Well, behind the scenes, you might know that might be calling a ping command in the shell, and there might be a chance to do command injection. So we'd say, hey, maybe if I put in a semicolon in a command, that can cause command injection. That's a hypothesis. Then in step 3, we'd actually go and try to test that out, or otherwise validate if that actually works, and see if we're right, if it's a valid hypothesis, or if it's invalid. And lastly, generalize it. So kind of say, what we discovered is this type of attack, and it's exploited through these means, and it results in this consequence or this exploitation. So that's kind of this formal hypothesis methodology from 1975 in a paper about computer or operating system penetration. So I'm going to kind of generalize that a bit more and say in practice, the first and really important step is to first of all, understand the system. You can't really attack it without understanding how it works. You'll want to define the system. What different parts are there? So let's say you want to look at a printer, a network printer. You've got different parts of it. There's like the scanner part. There might be a printer part, a network module. There's different components that have different inputs and outputs. And the interconnections between each part might be really important as well. And lastly on that, you want to define your scope. So what's in scope for attacking, what's out of scope for attacking. Second, you want to look for possible attacks, as I mentioned earlier. Identify areas that are exposed to user input, are exposed to uncontrolled information somehow. Those might be possible attack areas. Finally, you want to test those attacks and document what kind of attacks worked, what the result was, and how they can be replicated in the future. So I'm going to talk about my project I'm doing in 538, which is the reverse engineering class. And so each group got to pick a device for the class to purchase, which we will then try to hack into via various methods. And so my group is doing mesh routers. So mesh routers are kind of the new rage in home networking. So instead of having one wireless router that all your devices connect to, you place several of these mesh routers around your house, and they all kind of talk together, and they improve your signal strength and speed significantly, so they say at least. And we thought this would be cool to test because I did some searches online, and there's like almost nobody who's trying to hack into these things yet. They're pretty new, and there's lots of different points of entry on the attack surfaces. So, and we picked these TP-Link mesh Wi-Fi systems, and we got them actually yesterday, so I've not even opened the box yet. Yeah, question?
I just want to know, these operate on neural networks, correct?
No, so they don't actually use any special neural network technology. They just kind of connect together and balance out the Wi-Fi. So, oops, keep hitting the button. But yeah, so a lot of these new devices also have cloud components. So instead of going to the router's admin interface like you would with an old router, you go to either you install the app or you go to the manufacturer's website and it connects over the cloud. It's kind of complicated, but for our purposes, the cloud infrastructure is going to be out of scope. We don't want to attack the manufacturers or vendors' web properties. That's out of scope. That's illegal to attack. But the devices themselves are totally in scope and can be taken apart or attacked, broken in whatever way. So as I said, we just got these in the mail like yesterday, so I've not even opened the box yet, but I've already started trying to do some RE on them before even attacking them in person. So anyone have any ideas? What can we do before the box is even open? What can I do to start attacking these devices or to learn more about them? Any ideas what you could do?
Research.
Research? What kind of research?
Model, make, hardware, firmware.
Yeah, that's actually a good start. So the first thing I did when I selected this device was I went on the website of this device. And you can see there's a data sheet. That's all right. There's a manual. The data sheet tells us what kind of protocols or what kind of things it uses. So we can see it has parental controls, antivirus, some other stuff like that. It has an app for iOS and Android, Bluetooth. That's all interesting to know about the device. Just a little, intel from the website. Even more interesting, what do you see in this page that you'd want to look at probably? Anything of interest?
GPL code.
GPL code is one of them. Do you know what the GPL license is? So the GPL is the GNU public license, and it's the license used for things like the Linux kernel. It basically says that this code is open source, but you can reuse it you can modify it, reuse it, sell it, as long as it's still open source and retains this license. And so that means that this manufacturer has used open source code in their project, and they have to republish their changes or whatever they did with that code. So that might be very interesting to look at, since we'd see the source code for some of their components. They can still have their own proprietary hidden stuff, but that might be interesting to look at as well because it's open and we can just read the source code. Anything else of interest on here?
Firmware tab looks interesting.
The firmware tab looks very interesting. How'd you know where I was going with this? So yeah, right there we can download the firmware for this device. It comes in a zip file. I've noticed a lot of devices though nowadays. If you've heard of like the Eero mesh routers or the Google Smart Home routers, those don't have downloads for this. You'd have to like sniff their network traffic or something. But in our case, we're lucky. The manufacturer has provided us with firmware. And so with firmware, well, we pretty much have access to a lot of stuff. And I'm going to talk a bit about firmware RE here because it's pretty cool. So the first step is we've got this, well, I'll show you what we have here. So we've got this zip file, one of my terminal windows, yeah. So we've got a zip file. You can ignore all the other stuff on this terminal. That's from other experiments. But there's this deco M5 v1 version number or date or something zip file. So easy enough. Going to extract that. Oop. Interesting. Got to install the unzipper first. So we're going to unzip that. Okay, we get 2 files out of it. There's a bin file and the GPL license terms PDF, whatever. So this bin file is going to be what we want to look at. That's the actual firmware image. So let's see what kind of file it is. Using the handy Unix file command, it can identify files based on the magic numbers at the beginning. So it's going to try to match those against a known database of file types. And it just tells us it's data. That's not very helpful at all. Like, what do we do with data? If I try to open that in a text editor or something, let's see what happens. It's garbage, right? You can see some text in there, but it's mostly garbage. I don't know what to do with any of this stuff. There's also a utility called strings you can run on binaries that tries to print out basically any readable text. So if I do that on this, all right, I get some strings of interesting things. I don't know what any of it means. Really, this is all garbage to me right now. I can't do much with this. So what we're going to want to do is use a really cool tool called binwalk. So binwalk, according to its man page, it's a tool for searching a given image, binary image, for embedded files and executable code. That's really a huge understatement because binwalk is so much more than that, and it does so much work for you that it's just amazing. So we're going to use binwalk here to explore this mysterious file we have and see what's inside. So binwalk, got to install that too. This is a VM for this demo, so I've got nothing installed. Okay, I've got it installed on the host computer. We're going to install that in the background, but so okay, binwalk. So if I run binwalk on that file, we get a tons of stuff that prints out right away. So immediately the first thing is an ELF. We talked about ELFs last time in reverse engineering, right? So that's an ELF binary right there. We've got some certificates, some CRC tables, I don't know. This part's interesting. So we gotta have a gzip compressed file, and most importantly, a squashfs file system. That's pretty interesting. So the squashfs file system, it's a type of file system that you can use for like a Unix or Linux operating system root file system. And so that's going to be what we want to look at for sure. But how do we get to it? Well, binwalk, as the slide says, it's got this magic command, or I guess it's 2 separate commands, binwalk-e and -m, capital M. So the E is for extract. So if you run that on this file, so it's going to extract all of that stuff that it showed to us into a folder called, well, the original file name extracted. So in here, well, it's not the right one. Or is it? Yeah, I guess either way. Okay, so it extracted stuff for us. You can see here now in this directory, we have that ELF file on the far left. We have the squashfs image, some other certificates, and then it actually went ahead and extracted it for us anyway. I didn't even have to specify M. Normally M is for matryoshka, or whatever the word in Russian is. Oh, cool. So that means Russian doll, which, as you can see, Russian dolls you have a little bit slightly smaller one inside each one, so you keep taking it apart. And binwalk will do that with your file and keep extracting every file it finds until it can't be extracted any further. And that's pretty cool. So we just ran one command there, binwalk-em, or just -e in this case, and it went ahead and extracted all this stuff for us, and we have to do no further work to explore from there on. So as I said, we have these files here. If I look in the image directory, just certificates that pull out of that compressed file. Oops, we're kind of off the screen here. It's working apparently. Can you see at the bottom? No, not really. So much for auto image, right?
Just hit the projector screen down key, because I had put it up a little bit.
What do you mean?
Just press the down button.
That's what that does?
Yeah.
Oh, I thought it was all the, no, it's all the way down.
Oh, it's not. Oh, okay.
I don't know, but we'll be fine. So, as I said, the main part of interest here is that squash fs root. That's going to be the root file system of that device. And so on there, we're going to find lots of cool stuff. So does that look familiar at all? Some of those directory names. We've got our bin directory, dev, etc. A bunch of things you'd see on a Unix or Linux system. We've got our roots home directory. We've got a www folder for probably some website stuff. That's pretty cool. So we're on the target file system for this device we want to break into. So we can pretty much do whatever we want using that. We've got access to binaries if we want to look at binaries. If you want to do some binary RE, so we have /bin to look at. We've got a full load of different binaries in the system here. So you can see it's running BusyBox. BusyBox, if you haven't run into that before, basically it's a binary that provides lightweight, small versions of lots of common utilities. So BusyBox contains tons of things, like everything in this directory actually is going to be linked to BusyBox. As you can see, every file in there is a symlink or a symbolic link to BusyBox. So BusyBox implements, for example, copy. If you run the copy command, it's actually going to run BusyBox. If you run cat, it's going to actually run BusyBox. BusyBox just implements really small versions of these binaries for embedded devices like these mesh routers, so that when the manufacturer ships it, they just have to build a BusyBox instance that's customized with what they want in it, and then just ship that out, and it's pretty lightweight. A lot of these tools that you might be familiar with, the options with BusyBox are often quite restricted, so you might not be able to use the same command flags and stuff like that, but it's got a lot of stuff there. In bin, there's also sbin, as you'd expect, and then there's some more vendor-specific stuff in user local bin, I think. User bin, right. So some of that stuff looks interesting, like what's cloud? What are those cloud files? Those sound like they're very specific to this TP-Link device. There's also like TP-Link Apple, but with an S, TP-Link Simple, I don't know. Lots of interesting stuff there that you might want to look at. In addition to binaries, there's going to be configuration files. So we can look at in our etc directory a lot of the config files that ship with these devices. So you can see here, does anyone recognize what OpenWrt is? OpenWrt's basically a custom firmware, open source firmware for home routers that is quite powerful and quite configurable. And so it looks like that TP-Link decided to base their image off of OpenWrt, which is kind of exciting and kind of not at the same time. OpenWrt's already mostly open source or entirely open source, and so the code's already out there. So we probably didn't find too much new stuff with some of this, but now we know it's based off of OpenWrt, a certain version probably. But we can look at stuff like what startup scripts run when this thing boots. We've got a shell script here. This might be from OpenWrt, but yep, copyright openwrt.org. So that's not too interesting because we could just find that online, but if we find stuff that's specifically TP-Links, that would be more interesting because it would be specific to these devices. I should mention that TP-Link just had a bunch of vulnerabilities that were posted in the past year, so that's also a consideration for why we picked this brand of devices. They had tons of remote code execution bugs that came out recently, and we were wondering if this device maybe had some of those or newer ones as well. In addition to those config files, there's lots of specific scripts that run on these systems. So a lot of those functions, like when you're in the router's configuration interface and you say change the SSID, it might actually just run a script, like a shell script that does that for the router. And so that stuff's cool to look at to see how things are actually happening. And scripts are going to be plain text readable, so they're not you don't have to reverse them any further like you would with a binary. So if I look in, there's some stuff in, user bin here, I think. Well, as I mentioned, the file command is often useful to see what stuff is. I can run file star. And it's telling me a lot of stuff in here is BusyBox again, some other executables, but there's a shell script. What's that one do? What's sfe dump do? I don't know. So that's from Linux probably, but plain text code we can read here and start to figure out how stuff works. So what do we do next after getting to this point? We've got a firmware image. We can go to any directory on it. We can read config files. We can try to extract binaries to RE those further. We can look at scripts, pretty much anything. A lot of times vendors might leave default passwords and stuff on there that aren't documented. That could be interesting. But our next steps for this would be we could do some binary RE. So we can actually, since we have the file system and everything needed, we can actually run the binaries if we wanted to see how they operate or mess with them. I don't need that anymore. Oops. So, darn it. So yeah, if we wanted to run some of the binaries, we actually have to do something special first called a chroot. And this is because the libraries on the system, well, we need to use the libraries for these binaries. And in order to do so, we have to change our root directory to this file system here. Another note to pay attention to is that this is an ARM system. The chipset is ARM. My laptop's x86 64. So you can't just run code for a different architecture on your laptop. You have to use what's called an emulator. So QEMU is the emulator of choice in most cases. And so I can actually use this emulator, QEMU, to run ARM binaries on my x86 64 laptop. And so to do that, I've already copied over the QEMU static binary to this system. So if you look in, I think it's in user bin. Not there. Oh, there it is. Yep. QEMU ARM static. That's something I copied over earlier. And if I can run that to actually execute the binaries on this system. But what I'm doing here is I'm going to chroot into this directory, and bin.sh will be my command I run. That's the shell on the system. And you can see here we have a BusyBox shell. Now if you were to somehow log into the system itself, you'd get this exact same shell. We're running the shell on the device, the BusyBox ash shell specifically. And so we can pretty much do anything that we could on the system if we had access to the system. Built-in commands there. We could run different things. So if I wanted to run some of those scripts I found earlier, like bin login.sh, that sounds interesting. What happens if I run login.sh? It's a little slow because it's being emulated across architectures, but you get some ASCII art there. And if you, okay, so it's saying use password to change your password, right? This here is, I believe Chaos Calmer is one of the OpenWrt releases, so that's just probably some code from OpenWrt. Yep, there's a link to the wiki of OpenWrt. But we can start to poke around at these binaries, and we might figure out how something works. We could try to run some of the services on here and see how they actually operate. And further, if we wanted to actually find out stuff about them, we can attach a debugger to it, and I have a link here explaining how to do that. But the QEMU utility has a built-in GDB server, and GDB is the GNU debugger, which allows us to step through code and look at stuff like that. So if I run this with the dash, I believe it's G, and a port number, and the name of the binary, I believe it's in here. So I'm running UHTTPD, which is the web server on these routers. And so potentially I could open up a new terminal here and attach a debugger attach a GDB to that instance. Well, don't have GDB on here. It's all on my VM apparently. But if I were to do that, I could connect to that. Oops. The processes don't like to be killed very much. So I got a kill 9. But that would be very useful if we could attach a debugger. We could potentially see what's going on in that running process on the system. That'd be very cool to do. And as I said, we can just look around for sensitive information. You might want to run a system-wide search for files containing the word password or files containing other important keywords like backdoor or something like that. And so the way I see it is there's at least 2 approaches to proceed with this device at this point. So one way is we could kind of forget about the image, forget about our firmware for now, and start looking at how the web interface looks, seeing what inputs it takes, seeing how we can interact with it from the app or whatever. And once we find something that looks interesting, like maybe there's a certain field on the web interface, like I mentioned earlier, like a ping interface or something that could be susceptible to command injection, at that point we could go back into our firmware image and say, let's look at that part of the code that does the ping test. Let's look at that specific part of the binaries or part of the scripts that handle that. We could probably search through the file system for that pretty easily. The other way would be to spend all our time behind the firmware, looking at the binaries, looking at the scripts, trying to figure out stuff that way. That sounds a bit harder, in my opinion, because you'll spend all day looking at potentially assembly code or whatever you get it to, and you might not find anything. Whereas if you can find certain target areas that might be vulnerable, you can spend your time more wisely looking at the firmware when needed. So that's kind of what I'd probably choose to do on that one. And so as I mentioned, slides are kind of out of order here, but what I had to do if I wanted to ch root into the system and start executing those binaries, I had to copy the QEMU static arm to the target file system. I did a ch root to change my current file system root to that image, and then I ran the debugger. And then on the other machine, if I had GDB installed, which I'm sorry I don't, I'd run target remote localhost 1234, which is the same port that I had earlier. So that would connect us to that debugger, and we'd be able to profit off of our GDB foo at that point. So sometimes, though, that was an example of some really easy firmware to unpack and start taking apart, start reading every file in. It was just a standard squashfs file system. It was ready for us to extract it. Basically, there was nothing in our way from doing that. But lots of times, vendors don't want you to do this. They know that people are out there who want to reverse their firmware, find their binaries, find their proprietary stuff. And so they'll try their best to obfuscate or break or somehow prevent you from doing what I just did with that firmware. And so what I've seen here, I've got this device. I bought it for fun because the concept seemed interesting. It's a flash drive that has Wi-Fi. So you plug it in your computer, you copy files over, whatever, and then you unplug it from your computer, you turn it on, and it broadcasts a Wi-Fi hotspot, which you can connect your phone to or your computer to while you're perhaps traveling or something. And you can play all the media that's stored on here over this Wi-Fi network. So I'm like, wow, this little device is running probably Unix or Linux or something. Wanted to look at the firmware for it. So I have downloaded that as well. And this one is not very fun. I don't even know where to start with it. I've not spent too much time on it, but it's interesting as well. So same thing with this. If we run binwalk on this WFD, that's the firmware I got from SanDisk's website. The thing's called SanDisk Connect, by the way. I get all this garbage. So, okay, I get some images. I don't really care. Compressed data, more compressed data, images, lots of garbage. And then it identifies copyright strings and those look like base64 encoded text. I don't know what that is, though. And more copyright strings. So there's clearly a lot of code in here that they borrowed from someone else, which is okay. But that goes on for a while. And we get some HTML documents. And so I've already run binwalk on this, but I'll do it again, just for fun. So it extracted all that stuff to this same name of the file, but extracted. And inside, we've got garbage. So this is all the stuff that it listed in that binwalk listing. But if I run file on it, it's the same stuff again, some images or color profiles, compressed data. And the files that have no extension are the ones that were extracted all the way. So like there's 50d1d zlib, and above it's 50d1d. Well, this top one is this lower file extracted. So I've already looked at this stuff a bit, but it's like if you go into that file, it's either complete garbage and file doesn't recognize it, or some of these are HTML with weird other characters mixed in. That's not HTML. Some of them are HTML though. Question? Yep.
So it's all this partial garbage, but the machine still runs, so how can
Well, so my theory, as I kind of said in the slide, I think, maybe I didn't leave that in there, but what they're probably doing is that this is not the entire image on the device. This might be some kind of like update package that will only overwrite what changed on the device. So they don't give you the whole firmware. They just give it like a sort of like a delta or incremental update sort of thing. That's what I think it might be, unless one of these files actually is, you know, a binary or something. I mean, I don't really know what they are. They're, like as I said, the file command doesn't recognize them. I don't recognize them by looking at the headers. I would imagine file would do a better job than I would anyway of that. But some of these are, you know, HTML. So at most you could like modify the device's web pages and then install this firmware on it. You can't actually look at the firmware itself unless it's one of those files, but I've not yet found any way to do that. So that's kind of an example of times when manufacturers make it hard or maybe impossible to actually get the firmware. And so really it's not a fun day when you run into that. But a lot of devices are like the first one I showed, where you can just, you know, unpack it and it's good to go. A lot of home routers will be like that. I've not looked at too much other stuff, but that's usually what you'll see. So if all of that fails, if we can't, you know, get into the firmware, if it's not helpful at all, our next resort might be to go to hardware hacking. And we actually had a talk last semester in here about hardware hacking. But this will let us, you know, get a pretty good interface to the device. Serial is one of the most easy ones to interact with. We just have to find on the board where the serial pins are. You can solder 4 wires on there. Now you've got a console on the device. So like I had that BusyBox shell open earlier. That's what you'd see on the console. You're basically at the console on the device. It usually won't require login. A lot of times it doesn't. Sometimes it might, but at that point, you could start doing what I was just doing inside the firmware, except you're on the running device, and you could see what processes are running, what ports are open, stuff like that. That's really useful. You might want to do that in addition to looking at the firmware, since you can get an entire view of the device running from there as well. Although if you just have serial, it's kind of hard to copy files off of it because serial is pretty slow. I think one time I did it, it was like 8,000 bytes a second, so that's not very fast. Took a long time. There's also SPI, which can be used to reprogram flash chips and stuff like that. So if you wanted to overwrite something, a partition or something on the device, you could potentially use that to change it. I'm not really sure to the extent of what you can do with that, but it's fairly interesting. I should also mention with serial, you can look at the boot process. And so during that, there's the bootloader. So you can actually interrupt it and try to mess with its commands as well to potentially dump stuff off of it or do whatever, but that's also pretty interesting. The bootloader also might let you replace the firmware from there as well. And lastly, JTAG. You're kind of just overwriting memory on the chip, basically. So you can, if you were to break a device completely, like completely break the firmware, you could use JTAG to reflash it. Not sure if that'd be too helpful, but serial is what you usually want to go to if you're looking at hacking a device, the hardware style. So yeah, as I said, you'd be able to interact with the console, which is pretty useful. You could dump off the partitions if, let's say, the manufacturer didn't give you firmware. Well, now you've got a console on it. You can dump those partitions and maybe send them over the network to something else. You can actually start to do what I was just doing on the file system there. Or you could modify the system this way. Might not be as permanent, might be, depends on the device, but hardware hacking is definitely the next step to go to if you're stuck with the device and you want to learn more about it. So if even that fails, well, we're going to default to our typical attacks against all the inputs. So if the device has a web interface, we can go back to our standard, testing for command injection, testing for SQL injection, testing for anything like that we normally look for in an application, as well as attacking the network stack, scanning the device, looking for 0 days and stuff and the programs running on it. And we'll probably do a lot of this stuff anyway to verify if it exists or if we can get into it that way. But really, we're more limited this way since at this point it's a black box. It's not as open or it's not really as clear as it was when we had the firmware. So I know that was a lot of information at once, but does anybody have any questions or anything like that about hacking devices? Speak up now. All right, no questions? All right. Thank you. Slides will be in Google Drive.